Alright, these are my recorded office hours for Tuesday the 25th. I've had several questions that have been emailed to me, so I will address those, and we'll go from there. Alright, the first one I have is dealing with problem 3 on homework 1. So let me start my slideshow here. So, problem number 3. So in problem number 3, you have a shunt-connected DC motor that has a magnetization curve that's shown, and that measurement was made at 100 radians per second. And I tell you the RF, the RA, the R adjust, and the VT value. And you need to find the speed and torque developed when the power delivered by the motor is 3,000 watts. So that means my output power is 3 kilowatts. And there are no rotational losses. So you can assume then, because there's no rotational losses, that this is going to be the same as your developed power. And you're also told that it's operating in the normal operating range. Now, whenever you see any of my questions that have something along the lines, assume it's operating in the normal operating range, or assume efficiency is maximum, or something like that, usually it means there's two possible solutions, and you have to pick the one that makes sense. And so, first we need to, since we're told that this is a shunt-connected DC motor, first thing we need to do is find Kp if we can. And so, first we need to find the field current then. So the field current, of course, is going to be Vt all over Rf plus R adjust. And that's going to tell us the field current. Then, once we have the field current, we need to find from the plot our EA. Now, I'm going to go ahead and tell you what the IF is, so give you a little bit of a hint for your homework. This is 9.5 amps. So that's your current. Now, if you go to the plot, you look at 9.5 amps and read up on the curve, you'll see that's up towards the top where we start to get into some saturation effects. You read over, and you see then that your EA from the chart is going to be equal to 170 volts. Now, once you have that EA from the chart, you then can find Kphi, corresponding to that field current, is going to be EA from the chart divided by the omega m on the chart, which is 100 radians per second. Now, that's not the speed associated with your motor. That's just what you use to find Kphi. Let me make sure I'm recording here, because it's been a long day. Yes, I'm recording. So, that's how we find Kphi. That's the first step. Now, we need to find the speed and torque. But we don't know what, we're asked for both, and we only know the output power. And so, that makes things a little bit more difficult. However, go to the next slide, we know the developed power, the output power, in this case because there's no rotational losses, developed power is going to be the developed torque times the speed. So we know the product of those two. Now, if we go to the formula sheet, and we're dealing with a shunt-connected case, we know, for example, the developed torque has to be equal to Kphi, which we know, we've already found that, divided by Ra, which we know, multiplied by the quantity Vt, which we know, minus Kphi, which we know, times the omega m, which we do not know. That's just an equation for torque and speed for the shunt-connected DC motor. But let's substitute that equation into here. So we know that the developed power has to be equal to Vt times Kphi all over Ra. So that would be multiplying this term through here. And then I need to multiply that by omega m. And then I have this term here. So that would be minus Kphi squared, when I multiply that, divided by Ra times omega m for this case. And then, of course, I'm multiplying by omega m, so I have an omega m squared. So I know the developed power. I know that number. I can find this term. And I, of course, can find this term. So now what I have is a quadratic in terms of omega m. And so that has two possible solutions. which you can find the quadratic. So that's two possible speeds this thing could be spinning at and still providing 3 kilowatts of power for those voltages and everything that's been specified. However, we're told it's operating the normal operating range. So we not want the omega m that is close to the no load speed. Or we want the omega m that's the highest, because that would be the one that's closest to the no load speed. And so once we identify that speed, then we can, of course, determine from there what the torque would be, because we know the power, and once we know the speed, we can use this equation to get the torque. And there's other equations you could use as well. But that's how you solve problem 3. Okay, so the other one that was emailed to me, that was problem 3, was problem 5. That was the other questions that I had. And let me take a quick review of these. And so here they are saying they're having trouble when there's a gearbox. So they're fine with no gearbox, but when they add the gearbox, things are not working out for them. And I think I got another email along the same lines. All right, so the key to problem 5, when you add the gearbox, is figuring out what the torque is. And so gearbox has a ratio of 10. And so your output torque is 10 times your input torque. Now, we have to keep track of what's output and what's input. So remember, I need this thing to supply 50 Newton meters. So my output torque coming out of the gearbox is 50 Newton meters. That's what I need coming out. That means, in here, going in, I need 5 Newton meters going into that gearbox. So here's my gears. And so my output torque with the gearbox connected is 5 Newton meters. But I have rotational losses that I have to take into account. And I'm told that when there is when the gearbox is connected, I have 0.5 Newton meters equivalently of rotational losses. So this means my developed torque needs to be 5.5 Newton meters. Because it has to be able to provide 5 Newton meters plus the half Newton meter equivalent with the gearbox connected. So 5.5 Newton meters is my developed torque. And I'm assuming you were able to find K phi, because it's the same with or without the gearbox connected. That doesn't change anything, so my value of K phi is not going to change. And so once I have the torque, I can find the speed. Omega m has to be equal to Vt all over K phi minus Ra all over K phi squared multiplied by the developed torque, and that'll get me the speed of the rotor coming out of the motor. So that's the speed of the rotor before the gearbox. That's how fast it's spinning coming out of the motor. So that's what it means by coming out of the motor in radians per second. And then we need to find the efficiency. Well, in order to find that, we first have to find the output power. So the output power is going to be the output torque, which is the 50 Newton meters. That's my output torque, multiplied by the speed that it's spinning at. Well, the speed that it's spinning at is going to be the speed that I just found for the shaft divided by the gear ratio, divided by 10. It has to slow it down because you're exchanging speed for torque. That's how the gearbox works. So if the shaft is spinning at this speed, because of the developed torque being reflected through that gearbox, then this means that the speed going into the load has to be reduced by a factor of 10. So this is how we find our output power. Now we also need to find our input power to find out how efficient we are. And this, of course, is going to be Vt times If plus Ia. And so this is going to be then Vt times, we know If, because IF is what we use to find K phi, so I'm assuming you found IF without any trouble. That's, of course, is just Vt over Rf plus R adjust, plus IA. Well, what's IA? Well, IA is going to be the developed torque divided by K phi. That's the relationship we have for torque and current. And so, once again, this would be your 5.5 Newton meters. Add the K phi that you found earlier when you solved it with no gearbox connected, and then you're able to find then input power. And so your efficiency, of course, is going to be the output of power over the input power for your motor with the gearbox connected. And so hopefully that helps answer that question. And I believe that's all the questions that I had emailed to me. And so we'll go ahead and conclude these office hours. And if you have any more questions, please feel free to email them as well.